one result which occasionally comes in handy is the squeeze theorem for sequences. So the squeeze theorem, if you remember, for limits was this idea that if you had a function inside two other functions, one above and one below, and the one above and the one below were both going to a particular point, then whatever was inside also had to go to that point. Some people call it the sandwich theorem because the inside function, in this case we've got bn, is being sandwiched. It's like a sandwich, right, where the top and the bottom are the bread. So whether you call it the squeeze theorem or the sandwich theorem, the idea is the same. What you need to do is you need to show this boundedness, and then if both of those functions on the outside are going to the limit, then the inside one is going as well. So, and what you'll notice here, there's a for n greater than n. So that's sort of like it has to be bounded there eventually. If there's a finite number of terms at the beginning where it's not bounded properly, that doesn't matter. It just matters towards the end. But typically what we'll see when we use this is that it is bounded for all of the terms. One example of where you'd want to use this, let's say, is if I have something like this, cosine n over 1 plus n squared, right? Because this cosine n is going like everywhere, right? It's going everywhere. We don't really know what to do with it. But 1 plus n squared, as n goes to infinity, that should take everything to 0. So a very easy way of showing this is to notice that whatever we know about cosine n, it's bounded between -1 and 1. So my function bn here is bounded between 1 over n plus 1 and -1 over n plus 1, right? So, oops, n squared, it's n squared plus 1. So, this guy is my cn, this guy is my an. So, limit as n goes to infinity of an is clearly 0, right? Whoops. N is going to infinity. And then limit for my other guy is also clearly 0. So, limit of bn is equal to 0. So bn is that guy in the middle by squeeze theorem. So we don't have to use this very often, but every now and again, it's kind of nice to have that in your toolbox. Another sort of useful little result is the following statement. Let's see what I have here. And we actually almost used this already, if the limit of the absolute value of an is equal to 0, then, actually we didn't write it this way, but we could have used this, an is equal to 0. So if you remember in a previous video, we had something like -1 to the n, and what it was, 3n plus 5 over 4n squared minus 7. If I'm looking at the limit of this, remember we showed, so the absolute value is just going to be this thing without the -1. And we showed that that was 0. So if we had this theorem, we could just say, therefore, with the -1 to the n, it's going to be 0. Okay? So that's something that you can use for various things. Now let me actually go ahead and use it. I'm going to use it as part of a discussion that I'm going to have about an important limit. Okay, that important limit is limit as n goes to infinity of r to the n. Okay? So what we're going to ask is, what r can we use to get this to converge, right? For example, we already saw when we looked at just some pictures, if r was 2, okay, this diverges, right, because it goes to infinity. But when I had r being 1/2, right, this converged to 0. And of course, both of those are just things that you get from what's going on with, well, I can say e to the x, but I can call it b to the x, the exponential function, right? So if I've got b to the x here with b greater than 1, I know it's going off there. If I think about this, I can write this as b to the minus x, or I can write it as b to the x for b less than 1, right? Because it's just like writing it as 1/2 to the n. I could write it as 2 to the minus n. So we don't care about this part. Wouldn't have really bothered with that one. And there's also the special case here. This would be 1 to the x, which is just always 1. So since we know that about the exponential function from the little result that we had in a previous video, where what it does for the function of x, it's going to do for the function of n, as long as the function of n is, defined, we can see what's going to happen. So far we have this. If r is greater than 1, then limit as n goes to infinity of r to the n diverges to infinity. Okay? If r equals 1, then what do we have? We have 1 to the n, so this is 1, so it converges, right? It converges to 1. It's always 1. If r is between 0 and 1, right, then that's this guy. It's going to converge to 0. What about 0? Well, obviously 0 is always 0, right? So if r equals 0, then it also converges to 0. Because it's not going anywhere. It's always 0. Now, what about negative values of r? This is something that now we have to kind of use what we saw with that little theorem from before and maybe just a little bit of common sense. Because I can't take negative values for b, right? Because as we said, like negative 2 to the x, it's not going to make sense for every x, right? So, but what we can do is we can use what we had up there, that little theorem that I had before. If I've got r between negative 1 and 0, right, then what's this going to tell me? Okay? It's going to tell me what? So think about if I've got like a negative 1/2 to the n. Well, the negative isn't going to make a difference because when I take the absolute value, I'm here, right? So this guy equals 0 since the limit of n as n, that's an n, goes to infinity of the absolute value of r to the n equals 0 in that case. Okay? So if this equals 0, then that equals 0. Now what about n equals -1, or sorry, r equals -1? We know that doesn't work, right? If r equals -1, then we have the limit as n goes to infinity of -1 to the n diverges, right? Because it's -1 plus 1. It's bouncing back and forth. Okay. And then what's going to happen if r is even worse, right? If r is less than -1, right? So now we can think about something like -2 to the n. What is it going to be? It's going to be -1 to the n times 2 to the n. Well, this guy's going to go off to infinity. So what I'm doing here is, yes, I'm bouncing back and forth, but I'm bouncing back and forth between negative and positive infinity. So that's really bad. So I could just say, then limit as n goes to infinity of r to the n diverges. Okay. And I can do that basically by showing something like this. Okay, so there's a lot of stuff written on the board, but this is an important limit we need to know. So I'm going to try to distill it here of all of this stuff. So this limit is equal to 0 for values of r between -1 and 1. It's equal to 1 for values of r equal to 1. That's the only other thing here. There's always 0 or 1, or diverges otherwise. So that would be diverges for r less than or equal to -1, or r strictly greater than 1. So this is a thing that you should keep in mind, because we'll see it again and again, especially like also next week, a lot more we're going to talk about the geometric series.